When you type a query into a standard language model, it begins writing almost instantly. But that speed is actually its deepest structural flaw. The machine is not pausing to plan, structure, or verify its claims. It is merely predicting the very next word based on a mathematical average of its training data. If it starts down a path of faulty logic, it has no choice but to keep writing, doubling down on its own mistakes to maintain grammatical consistency. To solve this, researchers are building an internal loop of hesitation, forcing the machine to draft, critique, and edit its own thoughts before printing a single word. For years, the formula for building more capable artificial intelligence was brute force. Engineers gathered more text, bought more processors, and scaled model parameters into the trillions. But the industry has hit a thermodynamic wall. The internet is running out of high-quality human data, and the electricity required to train larger models is straining national energy grids. The premier reference point of modern AI scaling, a landmark survey published in Frontiers of Computer Science, highlights a critical consensus. Raw pre-training scale is no longer enough to drive intelligence forward. The industry is moving away from making the model's brain larger, shifting instead toward what is known as inference-time compute. This is the computational work a model performs after it receives a prompt, but before it displays an answer. Early attempts to make models reason relied on linear paths. Techniques like chain of thought instructed the model to solve problems step by step. While this improved accuracy, it remained incredibly fragile. If the system made a logical error at step 2, the entire chain collapsed, resulting in a confidently delivered error. The breakthrough came at the AAI Conference on Artificial Intelligence, where researchers introduced the graph of thoughts framework. Instead of a single straight line, this architecture models information as an arbitrary graph. It allows the model to generate multiple independent thoughts, combine them, evaluate their validity, and even backtrack to a previous step if it hits a logical dead end. To understand this mechanism, imagine an urban planner designing a transit system. Under a standard model, the planner must draw the entire network from start to finish in a single draft without ever using an eraser. If they place a bridge in an impossible location, they must still build the rest of the transit system around that mistake. Under the graph of thoughts system, every individual idea is written on a separate index card, which engineers call a vertex. The logical connections between these cards are represented by edges. An evaluator algorithm inspects each card. If a proposed subway line creates a bottleneck, the system does not throw away the whole project. It backtracks to the last successful intersection, discards the bad route, and attempts a new path. This self-refining loop is not a free upgrade. It introduces a massive economic and temporal trade-off. For a model to evaluate and refine its own thoughts, it must run dozens of internal prompts. This means that for every single word that eventually appears on your screen, the model may have generated and discarded hundreds of tokens internally. This causes latency to spike from milliseconds to 15 or 30 seconds. For a simple query like writing an email, this delay is an expensive waste of power. But as machine learning moves into critical domains where the cost of an error is catastrophically high, fast and cheap answers are no longer acceptable. Consider the delicate realities of geriatric medicine. Patients in this demographic frequently present with multiple, overlapping health conditions, a state known as multimorbidity. A study published in Aging Clinical and Experimental Research underscores how difficult it is to manage these cases safely. If a clinical assistant AI suggests a standard medication for an elderly patient's condition, it might overlook a subtle, dangerous drug interaction with their pre-existing heart medication. A standard, linear prediction engine can easily make this fatal omission because it cannot check its own work. A model equipped with an inner self-refinement loop, however, checks its suggestions against the patient's entire medical history, running simulated feedback loops to catch and correct harmful drug interactions before any treatment plan is printed. The inner loop also serves as a critical defense against adversarial attacks. Traditional language models are notoriously vulnerable to jailbreaking, where malicious users feed them clever, hypothetical scenarios to bypass safety filters. Because standard models generate responses on the fly, they can be tricked into outputting dangerous code or illegal instructions before they realize they have broken their own rules. A self-refining model operates differently. It drafts its response in a hidden, internal sandbox. An evaluator model inspects this draft for safety violations. If the evaluator flags any malicious content, the system quietly deletes the draft, refines the prompt, and outputs a secure refusal instead, preventing the exploit from ever reaching the user. This paradigm shift in software is fundamentally changing how microchips are designed. For years, hardware manufacturers built processors optimized for static, parallel feed-forward networks. Today, the demand is pivoting toward hardware designed to handle highly dynamic, graph-based search and self-correcting algorithms. We are entering an era where raw, unguided scale is no longer the metric of progress. The next generation of artificial intelligence will not be defined by how much data it has memorized, but by its capacity to slow down, question its own initial assumptions, and correct its mistakes before they are ever made visible to the world.